We use it to wash our hands, to cool off on a hot day, to take a bubble bath with a friend, to make a refreshing glass of lemonade, to power our houses, and to keep our lawns green. Water is the most abundant molecule on the Earth's surface, and it is vital for all living creatures to survive. But what about this mysterious substance makes it so useful and significant? To answer this question, we must look beyond the apparent aquatic attributes and investigate the secret life of water. As a first step, let's examine water on a molecular level. Water molecules are each composed of 2 hydrogen atoms and 1 oxygen atom, respectively giving it the molecular formula H2O. The hydrogen atoms are unevenly positioned about the oxygen atom, creating a bent-shaped molecule. This uneven arrangement causes water to have slightly positively and negatively charged ends, or what is called a dipole moment. These charged ends make water molecules attract each other. Substances with this type of self-attraction are called polar. No, not that type of polar. Water's polar properties determine its ability to mix with other substances. In this example, sugar is fully dissolved in water because it too is a polar substance. As a general rule, like dissolves like. Polar molecules bond with other polar molecules and nonpolar molecules with nonpolar molecules. In this second example, oil does not mix with water because oil is nonpolar. Even when they are mixed together rigorously, polar and nonpolar substances separate. How uncooperative. Due to its strong bonding, water molecules cling together. The force that pulls a substance to stick toward itself is called cohesion, and the force that allows a substance to stick to something else is called adhesion. When water drops are added to this penny, the molecule's cohesion prevents water from spilling to the sides. The skin-like property that water has at its surface is called surface tension. The effects of surface tension can easily be seen through this paperclip, that although is denser than water, rests on the water's surface. Surface tension can also be seen in nature through the ability of water bugs to walk on the surface of lakes and ponds. Now that we've examined the secrets of water on a molecular level, let's unlock the mysteries behind some of water's physical properties. As you probably already know, water can have 3 forms: a solid, liquid, or a gas. At standard pressure and temperature, water is in the most well-known form of a liquid. In this phase, water is essential, making up over 60% of the human body. When water is cooled to 0 degrees Celsius or put under extreme pressure, it freezes into a solid state, known as ice. When in the solid state, ice has a lower density than water, causing it to float in liquids. Large formations of ice called glaciers melt and provide us with clean, usable water. But if this ice melts too rapidly, it can, and already has, caused serious damages in the natural world. This time-lapse of melting glaciers shows some of the rapid melting of the Earth's ice. As a result, sea levels have risen, animals have lost their homes, and extreme weather conditions have become prominent. Water can also be present in the gaseous phase via the process of evaporation. This is commonly done by raising water's temperature to its boiling point and allowing it to transfer into steam. Through the process of condensation, water can also change from a gas to a liquid. Clouds are formations of very small condensing water vapor resting on dust particles in the atmosphere. When a cloud has more water vapor than it can hold, precipitation falls from the cloud and onto the Earth's surface. Once at the Earth's surface, it is crucial that water is purified before being used for drinking. First, water is purified via a natural process in streams. The water is then pumped to a purification treatment plant. At this treatment plant, water is separated and filtered. After being filtered, water is added with aluminum sulfate, which transforms into a sticky substance that attracts bacteria and impurities. The larger particles then fall to the bottom and are taken out of the water. It is important for water to also have the correct concentration of hydrogen ions that is safe for human consumption. The percent of hydrogen ions in the substance is measured via the pH scale. The scale ranges from 1 to 14, 1 being the most acidic and 14 being the most basic. The pH of pure water is smack dab in the middle of the reading at 7. In this depiction, a color gradation is used to indicate the approximate acidity levels. As you can see, vinegar is the most acidic, water is neutral, and bleach is the most basic. From clouds to faucets and glaciers to rivers, our world lives and can only function thanks to the help of water.